AP Chemistry, and welcome to the wave behavior of matter. So in the previous one, right, we talked about the wave nature of light, okay? And originally, for a long time, right, it was believed that light was its own thing and behaved in its own way, and matter was its own separate thing, right? Light not being a kind of matter, right? In that light does not have mass, right? Even when we came to the idea that light perhaps was composed of photons, right? Photons were a massless particle, right? That more described the transfer of energy as opposed to a type of matter, okay? Eventually, though, scientists came to the idea that perhaps matter also behaves kind of like light, okay? Meaning that it perhaps moves in waves, right? So de Broglie came up with the idea that wavelength is equal to h, which is Planck's constant, divided by mass times velocity, right? Or mass times frequency. I just didn't have the little new sign on this program. Anyway, so wavelength is equal to h over mass times frequency. Okay. So what this says here, right, is that all things that have mass also have a wavelength. All right. But what kind of relationship do they have? Right, they are inversely proportional, okay? Which means that as my mass goes up, and we start to talk about things we can actually see at a macroscopic level, as my mass goes up, the wavelength gets so small that we don't perceive it with our eyeballs, right? But as the mass gets tiny, 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 like to the point where we're talking about microscopic things, right? Then the mass is small enough that the wavelength actually becomes an issue, right? In terms of how it moves, what it runs into, and how it interacts with those things. Okay. Experiments were also done with electron diffraction, which is actually where the concept of our electron microscopes come from, right? Wherein, when we take light, for example, and shine it through a crystal, right, we get a specific diffraction pattern, right? The way the light hits certain parts makes the light turn at certain angles and create certain shadows behind it, right? Which is how we do like a lot of our X-ray crystallography, which allows us to determine the three-dimensional shapes of biological molecules. Okay, but somebody eventually got the idea. Well, why don't we try that with electrons? Right? Let's take electrons, right, and put them through a crystal and see if they diffract. And indeed, they do diffract, right? Which means that electrons, which we know to be particles, which we know to be matter, right, do also diffract. Right, meaning they travel in waves, just like light does. Okay, Werner Heisenberg came up with after all of this, the uncertainty principle. The Heisenberg uncertainty principle, right, which says that we cannot know both the momentum and the location of a particle. Okay, if something is moving, we cannot know both the location and the momentum of that particle, right? Which makes sense, right? Because if I know the momentum, right, the rate at which it's moving, right, I cannot know if I know the rate at one given point in time, I can't also know where it is, okay? And if we think about experimentally, right, we know experimentally where something is because of the track that it left, right? For example, we were just talking about electrons. When they get excited and they relax, they release a photon, right? That photon gives us information about where it previously was, where the electron previously was, right? Means we know a little bit of information about its previous location, right? But we can't know about its momentum, right? So it's just the idea that we can know one piece of information, but we can't know all of it, all right? Which is then going to bring us to the concept of orbitals, right? Wherein we can kind of know where an electron might be, but we don't know how it's moving, okay? So anyway, this is